So yesterday we were looking at the fundamental theorem of calculus, and we talked about two different parts of the fundamental theorem of calculus. And we looked at one part which helped us solve definite integrals without going through the method of using summations of rectangles. And we had seen that by one of the fundamental theorem of calculus parts that says if we have the integral from a to b of f of x dx, and this was a continuous function over a and b, then that means it's integrable, and this would equal the antiderivative evaluated with our upper bound b minus the antiderivative evaluated at our lower bound, which is a in this case. Then we moved on to another part of the fundamental theorem of calculus, and it really just depends on your book or who's lecturing or whatever. It depends on if it's the second or first part. This right here in your book was our second part, but I actually went over that first. And fundamental theorem of calculus can be abbreviated as FTC. Okay. So then we got into the second part, and the second part, or first part, depending again, was talking about the area under the curve. So let's just read through that again, and then we'll look through some examples. So it says that this, oops, wrong. I thought I had gotten my highlighter, but I didn't. So it says that the second fundamental theorem calculus says, let f be a continuous function on an interval from a to infinity. And that doesn't necessarily have to be to infinity. And we're going to define the function f on the interval a to infinity. So we're going to define that function, the antiderivative of f on a to infinity. And we define that antiderivative to be the definite integral from a to x of f of t. Then f is an antiderivative of little f. So capital F is an antiderivative of little f, and that is if I took the derivative of my antiderivative, I get back f of x. And so when we're doing these, we want our function, our value, our function to be on top. And we can manipulate it if it's not written that way by using rules of integration like we've covered before. So really, this is telling me right here, I want to find dy dx, looking at an example where we are, y is equal to the quantity cubed, and underneath that quantity or that cube is the integral from 0 to x of t cubed plus 1, and that's all raised to the 10th power dt. So notice when we take the derivative of both sides, this is the derivative. Let me just write that I'm going to take the derivative of the right-hand side. The integral from 0 to x, t cubed plus 10 dt. And that whole thing is cubed. So when I take this derivative, notice that I'm going to need to use the chain rule. So we think of that outer function to be this quantity cubed. And so when we take the derivative using the chain rule, we take the derivative of the outer. That's their question. So let me just pause. Okay, so when I brought my stuff down, I didn't copy it correctly. So this should be a 1 inside my integram. So that should be a 1, and that should be raised to the 10th. Thank you. Okay, so we're applying the chain rule, where we're taking the derivative of the outer of the inner. So let's bring that power down front. So that's 3 of the inner. I'll write that in a second. And we subtract 1 from our exponent. which is 2, times, then we have to take the derivative of that inner function. So d dx of this integral from 0 to x t cubed plus 1 all raised to the 10th power dt. Okay, so we took the derivative of the outer. We need to put the inner inside that derivative of the outer times the derivative of the inner. So now let's take the derivative of the inner. And we can use that fundamental theorem of calculus. And this is basically just, this was our integrand f of t. The derivative of that integral is going to be f of x. So let's just bring down what we have. So this is equal to 3 all times, all times 0 to x and an antiderivative of that, t cubed plus 1 quantity, that's to the 10th dt, times the derivative of this integral, which just gives us our integrand with respect to x. So that would give us times x cubed plus 1 raised to the 10th. Okay, so any questions on that before we go back and look at the one we didn't finish yesterday? Okay, so our next example is y is equal to, we have the integral with a lower bound is 0, upper bound is e to the x squared, all of 1 over square root of t dt. Okay, back up to the original, or the first one we did. I need to be careful because I'm dropping stuff off here and there. I need to bring the square down here. Square should be here. I missed it, or didn't bring it down. Okay, so back to this other one. We started this yesterday, ran out of time. The only difference with this one and the example that we did last, or with the fundamental theorem of calculus, was that this was just x, and this is a function in terms of x. And so basically what we need to do is when we're taking the derivative of this integral, we're going to plug in our upper bound wherever we see our t, but we also have to think about this as using the chain rule. We need to take the derivative of this inner piece that we're plugging in. So when we take the derivative here, we get dy dx is equal to the derivative of this. So by the fundamental theorem of calculus, that's just equal to 1 over square root. Normally we put the x there, but again, because that's a function in terms of x, we have to put this e to the x squared in here, times the derivative, and we'll come back and do that in a second, the derivative of the inner, which is e to the x squared. So we get dy dx is equal to, well, if I look at the square root of e to the x squared, that's just e to the x. If you don't see it, think of it this way, that we can rewrite this without the radical with a 1/2 power. Actually, is that not true? Yeah, is that not true? Hold on. Okay, so that would give us power to power squared times 2. That's just going to give us back e to the x. So I can rewrite this as 1 over e to the x. And now I need to take the derivative of this inside. So the derivative of e, and we're going to have to use a chain rule. So the derivative of e is the derivative of the outer, which is just itself, times the derivative of the inner, and the derivative of x squared is 2x. So cleaning this up just a little bit, we have dy dx is equal to e to the x squared all over e to the x times 2x. Okay, I gotta admit my algebra was wrong here. And now where did I put my pen? So this is not right. This would be 1/2 times the power of x squared, which would give me e to the 1/2 x squared. So this would give me e to the 1/2 x squared. And if that's the case, notice that these are the same base here. You have the same base, e. You have the same exponent, x squared. So we can subtract our exponent. So this would be, this is equal to dy dx is equal to, subtracting my exponent, so 1x squared minus 1/2 x squared. That's going to give me e to the 1/2 x squared times 2x. There we go.